Good afternoon, respected judges, fellow participants, and honored guests. My name is SUPANUN PATUMORATHAI from MUIDS. Today, I will present my project, Antioxidant Activity of Fruit peel waste using the dpph assay with a spectrophotometer and a home-built photometer. The main goal of this project was to evaluate whether a low-cost home-built photometer could produce results comparable to a laboratory spectrophotometer, making antioxidant analysis more accessible and affordable. Antioxidants protect our cells from free radicals. Fruit peels are rich in antioxidants, but they are usually discarded as waste. However, measuring antioxidant activity usually requires a spectrophotometer, which is expensive and not always accessible. To address this challenge, a university professor cooperated with us to develop a low-cost home-built photometer, and our role was to evaluate its performance through antioxidant analysis. The fruit peel experiment was used to validate our device. Our main innovation is demonstrating that a low-cost photometer can provide results comparable to an expensive spectrophotometer. Our objective were to compare the performance of the two instruments, evaluate the antioxidant activity of 3 fruit peels, and investigate the effect of incubation time. Our main materials included fruit peel extract, dpph solution, a spectrophotometer, and the home-built photometer. Fruit peel extract were prepared using ethanol and mixed with dpph solution. After incubating for 30 or 60 minutes, the absorbance was measured at 570 nanometer using the spectrophotometer. The same sample were then analyzed using the home-built photometer, which uses a single LED with a wavelength close to 570 nanometer, making it simpler and much more affordable. Both instruments show the same overall trend. As the amount of fruit peel extract increased, absorbance decreased, indicating stronger antioxidant activity. Passion fruit peel showed the highest antioxidant activity, followed by orange peel and lime peel. The 60-minute incubation absorbance values were slightly lower than after 30 minutes, indicating that the antioxidant reaction continued over time. However, the difference was relatively small, suggesting that most of the reaction had already occurred within the first 30 minutes. Most importantly, our home-built photometer produced results consistent with the spectrophotometer, demonstrating that it is a reliable and low-cost alternative for antioxidants analysis. This project has several practical applications. Fruit peel waste can be recycled into valuable natural antioxidant for food products. And since the home-built photometer is low cost, antioxidant research becomes more accessible for students, school, and laboratory with limited resources. It can also be used as a teaching tool for science education. These challenges that can be seen are some antioxidants may not have been completely extracted from the fruit peels, which could affect the results. Small measurement errors and dpph degradation from light exposure may also have influenced the experiment. Finally, although the home-built photometer produced comparable results, it may still be slightly less accurate than a laboratory spectrophotometer. In conclusion, fruit peel waste is a valuable source of natural antioxidants, especially passion fruit peel. More importantly, our home-built photometer successfully produced results comparable to a laboratory spectrophotometer, showing its potential to make antioxidant research more accessible. And these are my references. Thank you for your attention.
Thank you very much for your nice talk. So for this home-built photometer, you measure the wavelength at 517 nanometer. So can you also make this kind of photometer with that can measure different wavelengths? Is it possible?
If for antioxidant, it is possible, but it won't be as accurate as the 517 nanometer, since at this wavelength it absorbs the most dpph, like the light absorbs the most amount of dpph at this exact wavelength. But like if the wavelength shift a bit, like for example our home-built photometer, we use around 525 nanometer, which is more affordable and can be bought in some online platform. But it's gonna be less accurate, but it's still possible.
Okay.
Okay, so spectrophotometer is widely used device in research and industry. So here you apply this technique to measure antioxidant activity, but it can be applied to any other research. So in your home-built photometer, it can be only used at one particular wavelength, or it can be used to test observance at any other wavelength.
Currently, our phototype can only be used at around 517 nanometer, but in the future we might develop it so it can be used with other things other than antioxidant. Like for instance, the actual spectrophotometer can be used to research for the protein solution and other things, but right now we focus on antioxidants.
Okay, so here in your home-built photometer, what's the source of light, and how did you make it to emit only the light at 517 nanometer?
As I mentioned, it's not exactly 517, it's around 525 because that's what we can find and it's more affordable. And we cannot find the specific wavelength like the 517 nanometer in like ordinary shop. And our aim is to make this photometer the most affordable and accessible possible so it can be used in many things, like in laboratories that is limited in resources and funding.
Okay. Yeah, thanks.
Thank you very much for